What
Okay.
I'd like to do is just introduce my friend Brent Marsh, who's the CEO and chairman of Utricity. Brent is a 27-year veteran of invention, manufacturing, marketing, and implementation of clean technology. This happens to be Brent's sixth energy-related startup. During 10 years that he lived in Taiwan, he gained fluency in Mandarin and went on to manage a lighting controls electronics manufacturing company that gave him an experience with the product development and manufacturing and electrical systems. And I have to tell you that I'm always impressed with people who speak Mandarin or Japanese or something like that. I think that I could probably learn French if I had to, but I think it'd be a tough sell, tough deal for me to learn Mandarin. Was it hard for you?
Um, it was my third language, so I kind of figured out the process on how to learn languages early on.
Well, that's
Um,
it.
but yeah, after 10 years, it's pretty easy.
All right. Well, that's magnificent. I'm impressed. Let's go right into the subject matter here. So we're going to talk today about intelligent building management. And you know, I'm pledged to write a book every year on renewable energy, and I'm learning a lot more about it as I go, as you can understand. Um, but the more I learn, the more I realize that energy efficiency is really the low-hanging fruit here. So in other words, yes, we can generate clean energy and we can gradually replace fossil fuels in favor of wind and solar and geothermal and so forth and so on. But the to the degree to which, I mean, 40%, is it not true, Brent, that 40% of our energy is spent in buildings, and it largely, I guess that's lighting and HVAC. That's a huge component.
It is, and it's the one that's the lowest hanging fruit in the building, and especially with the advent of LEDs, and as they increasingly go into the building, you'll see that if 40% of the buildings, the electricity used in the U.S. is in the large buildings, and 40% of that is from linear fluorescence, then with the advent of the LEDs and figuring out how to integrate them, we have the opportunity to save 15 to 25% of the total building's energy use. So the impact is big. The paybacks are fast. And in perspective, there's about 1.5 billion fluorescent lamps that are in these buildings in the United States. So the opportunity is huge.
Yes, that's amazing. Okay, well, what we're going to do is talk a little bit about the business end of this. And so you believe that we're in the process of undergoing a change from, and I'll let you talk about this thing, from the ESCO model to this new thing. So talk about a little bit about what this will be replacing. So electric services companies, energy services.
Sure. Having been an ESCO, and then this is my third venture-funded energy efficiency company, I wanted to solve all the problems that were endemic in the early 90s when I ran an ESCO. And ESCO is Energy Service Company, and in the beginning it was just lighting companies that went in and changed out from T12s to T8s. And as the business grew, more sophisticated systems came out for HVAC and other building systems to find new ways to save energy. And then a lot of those opportunities went away after the buildings were retrofitted, and now we're going from, that was basically ESCO 01, ESCO 101. And so I wanted to develop a system that would take us to the next level, which was always the holy grail that people talked about then, which was selling light as a service, selling conditioned air as a service. And so that's why I think I've developed the system where we can move from the ESCO to the OSUS model.
Okay, so let's talk a little, before we get into this thing, so
Okay.
recognize that most of the people listening to this thing probably don't know a lot more about this than I do. So when you say you ran an ESCO, so the concept there was that you would go to a customer and you'd say, okay, let's just take your monthly utility bill. You pay me some fraction of what you're paying the utility company, and I will shoulder the risk associated with lowering that. Is that essentially what the ESCO model is?
That's what it is today. It can exist in two forms. I can, as a building owner, I can just say, hey, listen, find opportunities for savings, give me a bid, install them, and I will, and then, so the owners are bearing these operating costs from maintenance and electricity, and then the capital cost of buying the lighting. And so people would come in, put in the new lighting, and then walk away. But in the bigger ESCO market, that's where there's a concept known as energy performance contracts, energy savings performance contracts, and those require that the ESCOs at the government level, they come in and pay for the whole project all up front, as opposed to a commercial building owner who might pay for his project. For the federal government, the ESCO pays for everything and then they prove that there was a savings, and they share that savings over a certain period, and then the government buys it back for $1.
I see. Okay, so your viewpoint then is that we're in the process of migrating from that to this OSUS, you pronounce it, so on-site utility services, and that's where you get into this kind of more advanced type of use of information technology, is it not?
It is. It's not only information, it's a switch to DC microgrids within the building, as opposed to most people's concept are on a community basis or campus basis. But we combine DC at the circuit level and then also bring data, widespread network for all the building systems to talk to each other, layered with a sensor network where you can have granular feedback. And so we think it's a combination of all of those, as well as each device being able to self-meter itself.
Right.
It'll be easier to prove savings at the granular level, at the device level. And we think that the Internet of Things is really where the building intelligence and energy optimization is going to come from.
Okay, so walk us through, I know there are various slides on this, and maybe we're getting ahead of ourselves, but I just want to make sure that that I want to be a kind of advocate for the listener and for myself here, just learning as we go here. So what we're talking about here is an integration of, so you have a grid-connected building, but you also may have PV or wind on the roof or what have you. You may have battery energy storage, which may be performing certain things for you. So in other words, there is an incentive to have, we have DC integrated with AC, whether we like it or not, in the form of PV, let's just say, or batteries, right? So,
right.
So part of this thing has to do with recognizing that there are both direct and alternating currents associated with all of this stuff. Is that correct?
Correct. And if we look at how solar is done today and how wind is done today, for the most part, it's taking the direct current being produced and then converting it into AC, and then you sell it to the grid, and they sell it to somebody else, or you might be using the same electrons, but they're buying it from you if you're selling back to them at a fixed rate, but they sell back to you at a dynamic rate at various times of the day. And so also when you are inverting this, there is a loss, there's costs related to the inverter. So our approach is to take that DC that's being generated and drive it through the existing wiring and circuits in the building down to our DC-based LEDs. And so we take a high voltage, low current approach, and so we're able to use the existing wiring so that rather than sell to the grid at one price and buy back from them at another, why not just use everything you can make on-site as well as everything you might be able to store on-site, and then be able to arbitrage against the dynamic pricing that we see in the electric markets.
Good. So in other words, when you say arbitrage, you mean the typical thing of, essentially buying low, selling high. In other words, removing excess fat, excess profit out of a given market. Is that right?
Correct. There'll be, if we were able to drive, if we had enough roof space or enough field space to install enough solar, we could theoretically the entire day use that solar to power all of our lighting.
Right.
And the dynamics on reducing demand on your electric bill are just phenomenal. So if you could take potentially 40%, which is what the lighting is comprised of, off your grid every day, the impact for utilities as well as customers will be what we think is a huge, huge opportunity.
Okay, good. And I know I've seen this presentation, and I know this becomes more clear as we go through this. So here are some bullet points on the need for this for this OSUS. Do you want to just take us through this?
Sure. We think the path to energy optimization is using direct current products, because the way it's done today is you're buying from the grid at AC, and if it's digital, it's running on DC. And so we want to avoid all those conversion losses and directly power things with direct current. And there's a group out there called the it's eMerge Alliance, and they are also advocating DC microgrids in buildings, but they are in the 24 and 48 volt range, whereas we output 325 volt DC, which allows us to transmit over the existing wiring. So we had to choose the right voltage, and then that way we can, then with our power router device, we can take the on-site DC sources from the photovoltaic. It could be the dirty AC from a wind turbine. It could be battery banks that are distributed widely throughout the building. And so we can also take in grid AC and be able to dynamically blend them to optimize against the price of the market. Okay. And so to do that, we also needed this data network. And again, we were using Powerline Carrier, off-the-shelf Powerline Carrier chips. And so each of our lighting fixtures will get one, but then any other device in the building could conceivably have one of these chips that's added to it, and every device in the building will then have its own IP address, and then we'll know where it's at in the building, and so it'll also have its own fixed locational GPS address. And then we also use our lighting as a platform for attaching multiple sensors that also share those IP GPS addresses. And then that can provide feedback to all the other building systems, and then we manage it in the cloud, and we make it reactive to people, environments, and markets.
Very good. Very strong concept, it seems to me.
It's basically the Internet of Things for buildings.
Yes, right. Well, certainly the application, the assignment of an IP address to a device and using the cloud to manage these in real time is something that this is clearly the holy grail of intelligent building management, but it does seem that you have an interesting slice on this thing, given this application of DC and the kind of removal of all the losses associated with inversion of DC to AC, and then the power the power packs in all these digital devices.
And one key point I just wanted to reiterate, it's probably one of the cheapest and easiest things we can do in our system, but we can meter energy use in real time at the device level, at least the lighting level today. And then from that, we can prove to customers that we are saving exactly what we're saving and giving them that discount to the market. And that's really key to this, because the more you can measure, the more you can manage, the more you can finance.
Yes, very good. That it is true, and if you can't measure it, you can't manage it. Very good point. And this slide, if there's anything else you want to add on this one, here you're integrating the concept of a BEN, of a building energy network. Is this kind of integral to your whole concept, would you say?
Yeah, basically we have a server in the building that's connected to the electrical wires, and then these power line carrier chips that are embedded in our lighting. This network potential exists for any company that wants to do this, and that's the beauty of it. It's just we found the best application for embedding it in our system. Thus, we create this building energy network that, again, the whole building, all the building systems, any other third-party manufacturer wants to come in and provide a system that talks over this network. It's set up, it's ready to go, and we have the sensor feedback that's going to provide the granular data that they need. So yeah, it's very much the one part is the DC, one part is the network and sensor platforms.
Okay, very good. Here's another slide on the subject if you want to speak to this.
Yeah, the way it's done today is the customers are basically buying a product. It's either being self-financed or financed from the ESCO. We take a different approach where we want to sell light, air, and communication services that are cheaper than what you could buy from the market right now. And so what we want to do is take out the cost to the building owner, building manager, of having to buy lighting, of having to pay electricity for that, have to pay for maintenance, and we want to take all that away. We want to take out interest rates and credit ratings, and we want to take that part out of the equation so it's not just something they buy once for a certain price at a certain interest rate. We want to take away all that and give it all up front for no cost, but in exchange we want to sign a long-term contract, and we will continue to prove that we will be cheaper than the market. And so we will then put up our own on-site distributed energy resources. So we'll install the solar, the batteries, the wind, the fuel cells, whatever it might be. And based on the time value of electricity, excuse me, cheaper at night. We could charge batteries cheaper at night. We could buy excess wind power from the utilities at a cheaper rate, and then use that to run our appliances and devices within the large buildings in the daytime when the electricity is expensive. So because we're metering this, we can prove everything at the granular level. And so if today you were paying $100 a year for your CapEx and OpEx costs related to lighting per se, and I gave you a 10-year contract, for example, purposes only, of $50, would you take a 20-year contract to have a fixed rate, essentially? And so we've talked to a lot of people, and they do find that very compelling. And so people then will ask, okay, well, what after the equipment is paid off, why should I sign such a long-term contract? And we believe that from our sensor network, we will be able to derive large amounts of data that we can provide a wide array of different energy services and analytic services that they previously wouldn't have been able to even conceive of. And so we think through long-term the use of long-term photovoltaics, long-term LEDs, we can turn the light, air, and communication into a service. And we're not the HVAC specialists. We're not communication specialists. We are lighting specialists. But we think that this platform, other companies, third-party providers can come in and also layer on additional value over time.
Okay.
But yeah, so we want to turn it into a service rather than an expense.
Yes. Well, certainly there are a great number of business models that have gone in this way. You could suggest that even the ESCO types of things were heading in that direction, I suppose, by offering the building manager, kind of relieving him of the burden of worrying about prices over a long period of time. Here, however, obviously you've taken it to the next level, and it's interesting that you're talking about storage. Now, so large amounts of storage for uninterruptible power supply types of things are, of course, contemplated in most of our office buildings today, but not enough to do what you're talking about. In other words, to be able to store large amounts of energy, to buy it at off-peak times and to deploy it on peak. Is that integral to your concept? In other words, does this whole thing fail without that amount of storage, or is that just a nice to have here?
Storage is a nice to have item, and it's mostly not cost effective today for things such as time shifting of energy. But what we're looking towards is the secondary market for electrical vehicle batteries. So after they've decreased their value, they're decreasing capacity, we could still use them. They're small and modular. We can place them in electrical rooms on every floor of a high-rise building, per se. And so widely distributed storage at a smaller scale than what people are talking about grid-level storage.
Okay.
So we think it's much more achievable in the near term than and it will be cost-effective once energy prices rise to a certain point.
Okay, very good.
Yeah.
So I just put up this next slide. I guess we've kind of talked about this. Anything you want to add here?
Well, it's funny, the way today, and the way I understand it, power purchase agreements are fixed. The utility will pay you a fixed cost per kilowatt hour produced. But when they sell it back to you, you're getting charged at a higher rate depending on the time of day. So our motto is feed the loads, not the grid.
Yes, I see.
And so we can, by doing that, we can not only increase efficiency by a large factor, because we can, rather than today's method when the solar power is being inverted from DC to AC, there's a certain click-on period and click-off period. But there are still photons that are being converted to electrons in the morning and in the late afternoon, but they're not being used. In our system, because it's DC directly to DC, we can take in all those photons.
Right.
So it not only increases the efficiency there, but we don't have those conversion losses either. So it just makes more sense, we think, to feed the load as long as you can repurpose existing wiring from AC to DC, and copper doesn't know the difference. So, so we think it makes more sense.
Okay, that makes sense to me too.
Yeah.
Right. And here's one more on this.
We've
already talked about this for sure. So in other words, a big part of this thing is the efficiency gained by not having to do AC to DC and DC to AC.
Yeah, you've got the inherent conversion losses, because today if you just, the AC coming into your building is hitting a power supply and it's being converted to DC for whatever is digital in your building. And so not only do you have conversion losses, but then you have power factor issues and inefficiencies related to any particular power supply and particular application. And so when you're using DC, you don't have power factor issues. And it also, if you're going back the other way and you have photovoltaic and you're selling back to the grid, you have the cost of the inverter, you have the cost to intertie with the grid, and also you have anti-islanding issues, or islanding issues where if power goes down, the AC grid power goes down, your solar panel array gets turned off, so that when the linemen go back to fix the lines, they don't get shocked by all the solar being injected back into the grid.
Right.
So you would think that it would be great, the sun's still shining, power's out, that you could still have light. With our system, it can.
Yes, good point. So, and this power factor thing is a big deal in commercial buildings because commercial customers pay for a penalty for power factor, don't they?
Correct. Yeah, it's like two sides of the same coin. Power factor, in residential you're paying by the watts, but in commercial settings you're paying volt amps, and that's where power factor comes in, and they charge a penalty for a lower power factor. But with DC in our system, we're basically 99.9% power factor, so we don't face that penalty. And then on the flip side of that coin is total harmonic distortion, which causes resistance in the transmission lines, and so they have to opt for larger wires to accommodate bad harmonics. So when you have good power factor, you also have good harmonics. So the utilities, they're very much in favor of good harmonics.
Right. As a matter of fact, I think this, let me just slide here. This is the one, if you want to talk technology, you might as well speak to this.
Yeah. We have a, what we consider a simple three-part system that enables this OSUS model. We start with our DC power router. We have a 6 kW unit, and it can dynamically blend DC and AC sources, and we output 325 volt for almost all the world. The only reason we output 430 volt is because today the bulk of lighting circuits in large commercial buildings operate at 277. And it's just so how the math works out, we have to put out 430. But for the rest of the world, where with voltages between 100 volts in Japan, for instance, up to 240, and 230 in Europe, 50, 60 hertz, we would output 325 volt to create this global meta voltage, at least for the lighting. And incidentally, this anyone who wants to ask later on, they can find out why is it that 325 is such a special voltage. It's because it is the peak of 230 volts. And so any power supply with the 100 to 240 input, we can inject 325 volt DC into that, clean up power factor. And we think we have a large amount of emerging DC devices that we could either drive from 325 or step down and increase efficiencies. So this power router, it gives us the ability to take on-site resources like batteries and fuel cells and solar and directly inject them down to our lights. And so one of our units can power up to 400 lights. And what we're doing is we have a linear fluorescent lamp replacement using LEDs. And so they're being run at 99.9% power factor, and we have minimal power conversion, power losses. And if you opted and you had enough space for batteries and solar or your other sources, you could be completely grid independent using our system as well. And yeah.
Good. So here's we kind of skipped ahead, but let me go back to this overall system diagram. Do you want to just walk us through this?
Sure. If you look at the top left, you have your distributed energy resources, which include batteries, solar, wind, fuel cells, whatever else. I put a link on there to a Geico commercial showing a man who developed a system to generate electricity using guinea pigs. That might be also one of the things that goes up there. But basically, those DC sources are fed directly through our power router. And at the bottom, you see grid AC also being fed into it. And this box, a little bit bigger than the size of a shoebox, gets mounted right under the circuit panel of each specific, say, lighting circuit. And we inject DC down to the existing wiring, down to the existing fixture. And we replace the ballast with our drive box, same footprint, and then you remove the old fluorescent lamps and put in our lamp. And so one power router can power up to 400 lamps. At the same time, each drive box has its own power line carrier chip with its own IP address, GPS address, and it is a host. We have several Ethernet connections where we can plug in lighting sensors for controlling the lighting, or we can put in temperature, humidity sensors to feed back to HVAC systems, or we could use it as a power hub and plug in wireless nodes such as Wi-Fi or Zigbee or Bluetooth or cellular repeaters. So we could use our drive box as a power hub as well as a sensor hub. And so basically with our lighting in place, it has its own standalone value proposition, saves so much money, it's intelligent, its ultimate efficiencies can be run from distributed energy resources. But with our lighting in place, we've established the network and the sensor platform that we think is the lowest cost way to spread intelligence throughout the building, as well as provide this global meta voltage, which can be used with a wide variety of AC equipment and DC equipment. So we provide the platforms for the whole building optimization.
Right, very good. And here are a couple of other kind of summary slides about the company Utricity and its approach.
If we could, you have a slide there on the lamp. I wanted to talk about that and why this lamp really sets us apart. I think this is an interesting thing for people out there who like LEDs. Yes, very good. And I think it's this one right here. Right there. So we have, I think anybody in the lighting industry has probably seen a lamp. This is a bad rendition of it, but basically LEDs put into an array inside of a tube that looks like a T8 lamp. Ours looks just like hundreds of other ones out there you've seen, except that ours doesn't need heat sinks. Ours doesn't need drivers. We can dim down to 2%, and because our power router can power up to 400 lamps, we have the lowest power supply cost per lamp. And so the reason I mention this, and we drive it at less than rated operation, so we have an extended lamp product with a higher efficiency. But the reason I mention this is that we've taken this high voltage, low current approach to driving low power LEDs, contrary to what everybody else is doing with high power LEDs. So we just do not generate the heat. We only have, total lamp only has a heat rise of 26 C at the junction temperature above ambient. And so the balance of system costs for making an LED comprise about 60% of heat sinks and drivers and power supplies. And the other cost is the actual LED. Well, the market expectations are that the cost of LEDs will drop about 90% in the next 5 years. So without the needs for the cost of those other systems today nor tomorrow, we think we have a new approach to LEDs, and we can reconfigure this into multiple new different applications. And so we think we have a breakthrough LED product that really makes the whole entire system cost effective, that realizes allows us to realize this OSUS concept. So it's really this lighting technology and how we drive it is really what sets us apart, and why this is more than just a cool idea on how to make buildings more energy optimized.
Good. And here's a little summary on the drive box.
Yeah, so again, we wanted to, having run an ESCO, I wanted to design something that was same footprint and installation method as what the guys are up there doing the retrofits already. So this isn't an actual device, it's just a picture of a ballast, but it'll look just the same. We'll have input wires the same wiring. Instead of AC going in, it's going to be DC going in. And we'll have a tiny logic power supply that will drive the PLC chip, as well as provide power to the other sensors that we can plug into that with Ethernet standard RJ45 connectors. And so we'll be able to dim at the fixture level. So each fixture can have its own dimming policy and be demand responsive, or be dimmed through sensors. But then more importantly, or as important, is, as I mentioned before, we're able to, because DC is much easier to measure than AC, we can measure energy use at the fixture level, and we can also use that same RJ45 connector using power over Ethernet to power wireless nodes throughout the building. So we want to transform the existing infrastructure into a whole new platform for proliferating, sensing, lighting control, and enhancing wireless proliferation in the building.
Well, that's good. And I wish I could give you more good news and give you the slide that you wanted here. Unfortunately, this doesn't, I've come to realize this doesn't display that table. Brent, this is supposed to be your table on the savings analysis. Do you mind, can you just speak to this verbally?
Yeah, we, just off the top, our system, we don't look at this so much as a lumen, how many lumens our lamp puts out, and how many foot candles is required by code per specific application. So this was an example of what was required for stairwells and parking garages, and the use of being able to attach an occupancy sensor, and assuming that 80–85% of the time nobody was there, but due to code requirements, there had to be a minimum amount of light, and when someone walks by, it's on 100%, and when someone's not there, it's at 10%. We showed in New York, with New York and California markets, we can provide a 1 to 1.5 year payback period, including incentives, rebates, things like that, but under 3 year. And if we can bring that same capability, we can also prove all those savings. But again, the same unit we could also have it networked for demand response. So we think that the initial example was a 24-hour application, which of course had the fastest payback periods. But adding demand response and the ability for ambient light dimming, we think we can deliver similar kind of savings with, in the 2–3 year payback period once we get into the building as well. And again, this is just for the lighting benefit alone, but with the lighting comes the sensor platform, comes the network, comes the potential for integration with direct current and on-site distributed energy sources.
Great.
So,
very good.
Yeah, so this is a concept I'm calling photons to foot candles. Going back to a bunch of things I was talking about in the price differentials, where today how the market works to selling to the utility the fixed cost that you're buying back from them at a higher dynamic cost. Just so happens that those higher costs correspond to when PV is actually tracking. So when the electric rates are high, if we can directly use them and cut demand, we can dramatically lower energy bills that way. And if you happen to be, say, a military base and you had lots of room to put PV, you could be a net positive energy entity and actually run your facility, store on site, or sell back to the grid. And so this could give you UPS capability with widespread, widely distributed battery arrays on small scale. We can do demand response. So rather than turn off mission critical lighting, we can still offer demand response by running off the batteries. And then since we can do this in real time and give feedback in real time, rather than the 15-minute intervals that are faced today by the smart meters, we can offer frequency regulation and load shaping, shipping, and other ancillary services to the market. So the value goes up even more once you start considering what utilities, what you can charge in the wholesale retail electric markets. And of course, if you have enough space for all this stuff, you can be grid independent, which is one of the goals of the U.S. military, because we don't want to be dependent on if the grid went down for more than a week or two. I think all hell breaks loose. I think there's a theory, 10 days without electricity, then civilization ends. So I think the military has a big reason to stay operational, and they have the space to do that. And we think this system is particularly well suited for that sort of thing. So one day, what we see is an increase in efficiencies in PV and LEDs in batteries. And while we'll also see a decrease in cost over time. So
right, which is good for you as an organization participating in this, because you have, that's part of the business model, in other words, for you to capitalize on the fact that costs will be coming down. Is that not correct?
Right. If I could sign a long-term fixed contract today that makes sense to you in the short term and the long term, but my cost to deliver it go down over time. For instance, every photon being converted into an electron that's going through my system to be reconverted into a foot candle. What will that cost be over time? And so we've been running some numbers, and we think the photon to foot candle conversion cost can come down also somewhere in the 60 to 90% in the next 5 years. And so that even further supports the idea of selling light as a service. Air is not our business, communication is not our business. We just have the platform. But the idea of converting, it's a little concept they came up with called inside sun. Basically, how do you bring the photons from the sun down and convert them into the photons, the lumens, the foot candles inside the building.
Yep, so, clever concept. And then here's a kind of summary slide on the market opportunity for Utricity. And you might want to add, as you're discussing this, is this an investment opportunity, Brent? In other words, are you looking for investment capital to move this forward?
Yes, we are. We're in fundraising mode right now, and we've generated interest from NASA, from Google. PG&E saw the value in the demand response and the occupancy sensors for stairwells and parking garages. We've had interest from 3 of the 16 super ESCOs that do all the government and military projects. And we've had recent discussions with Chinese provinces, investors, manufacturers, because they are on a path to spend trillions of dollars in the next 10 years, with energy efficiency being one of the big 7 in their smart city, smart grid efforts that they plan on implementing in the next 10 years. And I just came back from a trip there after they had just announced their 12th 5-year plan. And their goals are very much, they use the term the Internet of Things for buildings, and very much like this concept of photons to foot candles and bringing DC directly to the DC lighting. So, the opportunity is huge, because I think outside of the standard screw-in A-lamp, the linear fluorescent lamp is probably the most prevalent electrical device in the world. And particularly in buildings, which is our target market. And so, we've got 1.5 billion fluorescent lamps in the U.S. you can only imagine 3 to 5 times that amount for the rest of the world. So this is an easy entree point into establishing these building energy networks, the sensor platforms, and the integration of distributed energy resources. So, yeah, we think the market opportunity is huge, and we're going to be putting up a LinkedIn site around OSUS, around this photons to foot candles, because we'd like to have other people help experts in solar systems and in batteries and in LEDs. Let's figure out what will the cost of photon to foot candle be in the next 5 years. What will the potential for storage be on a widely distributed basis? So I'd like to get a little crowdsourcing help because, like I said, we're not experts in everything, but we think we've got a good idea to move this thing forward. And I think with the advances in technology in the next few years and the effort and money going into it, the economies of scale are going to be so large that the world of energy in a few years is going to look so much different than it is today. And so I think we're poised to take advantage of those trends better than probably anybody else out there that we've seen. So,
well, I certainly agree. I thank you so much for doing this, Brent. Nice to speak with you as always. And certainly anybody who's interested in speaking with Brent about this as an investment opportunity, just hit contact and I'll make sure that you're connected immediately with Brent. And anything you'd like to say in closing?
I just want to thank you, Craig, for the opportunity and the chance to reach out to your people and see what we can do in the future. And after all, we're all interested in this to save the planet. So let's get together and see what we can do.
Like it very much. Thanks again. Talk to you again soon.
Okay. Bye-bye.
Thanks. Bye, everyone.